So we have seen that the warping function satisfies this particular equation, right? And so whenever xi satisfies this particular equation, it is said to be harmonic. And so when xi is harmonic, so that means it satisfies this particular equation. When xi is harmonic, there exists a conjugate harmonic function G, which is related to xi by the Cauchy-Riemann equations. So del xi by del x is equal to del g by del y, and del xi by del y is equal to minus del g by del x. So these are what are known as the Cauchy-Riemann equations. So if xi is a harmonic function, that means if xi satisfies this particular equation, del square xi equal to 0, then there exists a conjugate harmonic function g, which is related to xi through these equations, the Cauchy-Riemann equations. And the boundary condition now will be given by, so we have seen that y and x minus x and y now will become, so you get that y and x minus x and y will be equal to y times dy by ds plus x times dx by ds, which is equal to del g by del y times dy by ds plus del g by del x times dx by ds, which is equal to d times g by ds. So this condition is obtained from the expression that del xi dot n. So this particular term is obtained from del xi dot n. So that is del xi by del x. So instead of del xi by del x, you substitute del g by del y. And then from that you will get this particular expression here. And this here is this y and x minus x and y. So this is what you will get. And then so from this condition you will get that this will imply that g is equal to x square plus y square divided by 2 plus some constant. Right? So this can be expressed as d by ds of x square plus y square divided by 2. And so this whole thing is equal to dg by ds, and so you will get g is equal to x square plus y square divided by 2. So basically now your governing equation and the boundary condition for this function g is given by, so you will get that del square g is equal to del square g by del x square plus del square g by del y square is equal to 0 on A, and g is equal to half of x square plus y square plus some constant on C. So this is A is your domain and C is the contour of that particular surface here. So this particular problem is a Dirichlet type boundary condition, right? So this is a Dirichlet type boundary condition. So we saw last time that there are two types of boundary conditions. So for the xi function, we saw that del xi dot n is equal to y and x minus x and y. That is a Neumann type boundary condition, because as I said that there the boundary condition involves derivatives of xi. Whereas here you can see that the boundary condition is directly on the g function here, and so that is a Dirichlet type boundary condition here. And the solution to this Dirichlet boundary value problem is also unique. Okay, so solution is unique. So solution is unique. So again, actually, so if you fix this constant, then the solution is unique. Okay, so you can fix it. So how to fix that we will see. But at this stage, for simply connected domains, you can simply take this constant to be 0. So simply connected means that there are no holes in this particular cross section. So if it is a simply connected domain, then you can just simply take this constant to be 0. And so most of the times you will be just considering simply connected domains. So I will just mention how to solve the problem for multiply connected domains at a later stage. But at this stage, we can just take it to be a simply connected domain here. Then the expressions for the stresses in terms of this function g are given by tau xz. Now tau xz is equal to g alpha times del g by del y minus y, and tau yz is equal to g alpha times minus del g by del x plus x. So initially we had expressed this tau xz and tau yz in terms of the xi function, and now what you do is that in place of the derivatives for xi, you replace it with in terms of the derivatives of g, and so then you will get these particular expressions here. Yes, and another thing to note is that no matter what constant you choose here, these expressions for the stresses will remain the same. This is g. The expressions for the stresses will remain the same because because it involves derivatives with respect to g, and so the constant is not going to matter. So as I already said that if it's a simply connected domain, we will simply take g is equal to half of x square plus y square on this outer boundary here. Okay, fine. And then so we have seen that the functions xi and g, they satisfy this Cauchy-Riemann equation. So one way of generating this xi and g is by taking the real and the imaginary parts of a complex analytic function. So you have probably seen this approach in your fluid mechanics course when you are doing the ideal fluid flow, the potential function and the stream function, right? They are the real and the imaginary parts of a complex valued analytic function. So this is very similar to that. So let us look at that, how to generate the two functions xi and g. Since the real and the imaginary parts of a complex valued analytic function z, where z is equal to x plus y, satisfy the Cauchy-Riemann equation. This y equations we can take z as equal to xi plus ig. And by choosing different analytic functions of z, like let's say z square or z cube or whatever, log z or different types of analytic functions. So if we choose different types of analytic functions in z, then the real and imaginary parts of that complex valued analytic function will give us the warping function and the conjugate function g. Fine. Then in addition to these two functions, xi and g, there is also a third function which is known as the primary stress function. Okay, so in addition to xi and g, the third function known as the primary stress function. Denoted by phi can also be used, and also so basically you have that tau xz is equal to del phi by del y, and tau yz is equal to minus del phi by del x. Okay, so basically, if you write it this way, then the del tau xz by del x plus del tau yz by del y equal to 0 is automatically satisfied. So if we just substitute, tau xz is equal to del phi by del y and tau yz is minus del phi by del x into this equation, you will see that this equation, the equilibrium equation, is automatically satisfied. Okay, but then now what you can do is you can equate these expressions for tau xy for tau xz in terms of the warping function and in terms of this primary stress function. So what you will get is that tau xz now is equal to del phi by del y is equal to g alpha times del xi by del x minus y, and minus, so similarly tau yz is equal to minus del phi by del x, that is equal to g alpha times del xi by del y plus x. And so if you eliminate xi now, so eliminate xi, then what you will get is that del square phi is minus 2g alpha. So this is the governing equation for this function phi here. And if you now substitute it into the boundary condition, so that is tau xz nx plus tau yz ny is equal to 0. Correct? So tau xz nx plus tau yz ny equal to 0, and then if you substitute for tau xz and tau yz into this particular expression here, you will get that this is del phi by del x times dx by ds plus del phi by del y times dy by ds is equal to 0. So this implies that d phi by ds is equal to 0. So this implies that phi equal to constant on C. So again, the same comment that I made about the function g is that you can choose that constant to be 0 if it's a simply connected domain. Okay, so because the choice of the constant is immaterial, so you can just choose it to be 0. Okay, for a simply connected domain. If it's a multiply connected domain, then of course there are complications, so we will look at that later. So basically So what you have is that del square phi is minus 2g alpha on A and phi constant on C. This is again domain A and C. So this is the governing equation and this is the boundary condition which is satisfied on this. So actually this function g and the function phi, they are related. So you have that g is actually equal to half of x square plus y square plus phi divided by g alpha. Okay, so this is the relation between g and phi. So you can directly, so the proof for this is just directly you can verify that del square g is equal to 0 because del square phi is minus 2g alpha. And you can see that phi is 0 on the boundary, right? So you will get g is equal to half of x square plus y square on the boundary here. So, so from this you can directly see that this particular relation between the two functions g and phi is satisfied. So this is also a Dirichlet type boundary condition here that phi, because directly you have a boundary condition on the function itself rather than on some derivative of it. So similar to g, this boundary condition is also a Dirichlet type boundary condition. Now we can get a very nice expression for the torque in terms of this phi. So let us look at that. So T is equal to integral of A of minus of x times del phi by del x minus y times del phi by del y times dA. This expression is that y times tau xz minus x times tau xz, right? Integral dA. So that I derived in the last class. So all I am doing is that I am substituting the expressions for the stresses in that particular expression, and then we will get this particular expression here. And this we can write as equal to integral of 2 phi minus del by del x of phi times x minus del by del y of phi times y, the whole thing times dA or A. Okay? And so this is equal to 2 times integral of phi dA minus integral of phi times x and x minus plus y and y times dA. So, so actually again, if you take a simply connected domain, then we know that phi can be taken as 0 on the boundary because there are no holes now, and just on the outer boundary because the constant can be just chosen to be 0, you will have phi equal to 0 for a simply connected domain, and so this integral will vanish and then you will get that this is equal to 2 phi. So since phi equal to 0, so for simply connected, so for simply connected domains, you have that phi equal to 0 on C, and so this will imply that T is equal to integral of 2 times phi times D. So this is a very, very nice expression for a simply connected domain here. So just the integral of phi times dA multiplied by 2. Fine. So what happens if you have multiply connected domains? Okay, so let us look at now the case where you have multiply connected domains. So in that particular case now, let us take this domain, and now these are various holes that you have. So you take phi equal to 0 on the outermost this one, so then that be C0, and now you have C1, C2, C3, these are the various holes now. And so this so the constants now, so this will be phi equal to K1 on this particular boundary. Now this will be phi equal to K2 on this particular boundary, then phi will be equal to K3 on this particular boundary, and so on. Okay, so now these constants cannot be chosen to be 0, right? Because we have already chosen the outermost constant to be 0. But now this is relative to that, right? So you cannot choose now these constants to be 0. So these, let us call them as A1, A2, A3 and so on here. And this nx tilde, so let us call this normal as nx tilde and y tilde. These are the components of the normal which is pointing inward into the domain. Okay, so into the hole, because this normal is actually the outward normal to the domain, right? Because the domain is the part of the domain which is excluding the holes, right? And so the outer normal to that will be actually the inward normal to the holes themselves. And let us call it as nx tilde and y tilde as the normal that points inwards. And that will be equal to minus of nx and y. Suppose if I take the outward normal to the holes, then so let me just write that here. So nx tilde will be equal to minus nx and ny tilde will be minus ny, where nx and y are the outward normal to the holes. Okay. So nx tilde and y tilde are the components for the normal that is pointing inwards, and nx and y are the components for the normal that is pointing outward for each of these particular holes here. Fine. So I can write now. So using that expression which I had, this is 2 times phi times dA plus summation I equal to 1 to n. So n is the number of holes now. So that is times ki times integral of ci of x and x tilde plus y times ny tilde times ds. So this is what you will get. And if you now write this in terms of the dx by ds and dy by ds, then you will get that so this is equal to 2 times integral of phi dA plus phi dA plus summation I equal to 1 to n ki times del x by del x plus del y by del y times dA. So this I am just applying the divergence theorem here. I think I have just made a slight error. I will correct it. Actually, this nx tilde and ny tilde is for the outward normal here. I am sorry about that. So here, actually, the so a little bit of confusion here. Let me redraw this figure here. So suppose if this is the hole, then nx and y is this particular normal, and nx tilde and y tilde is actually this particular normal. I'm sorry about this confusion here, but now I think this is okay. So see, nx and y is the normal to the holes, and that is the outward normal. Now nx and y is the outward normal. Okay, and so let me just call it as an outward normal to the holes at the domain, and then nx tilde and y tilde is what points inward now into this one, but it is the outward normal for the holes. So just the notation got switched, but now it is okay, I think here. And yeah, I'm just applying the divergence theorem in this particular case. So here you can write this as x, y dot n, right? And so this will be del dot of x comma y. And that will be given by this particular expression here. And so this is equal to 2 times integral of phi dA plus 2 times summation ki. And now you can see that integral of dA, right? So this will be just 2. So you will get this 2 here, then summation ki. And then this will be just integral of dA here. So this is an integral over A. So you will get simply AI. So this will be the expression for the torque in the case of a multiply connected domain. So this Ki is the value of the constants here, and the AI is the area of this particular holes here. So basically, let me just draw the picture. So suppose if you have a single hole here, and then this is the thing, and then now if you draw the phi function, so it will look something like this here. So this is your phi function, and then this is the value of the constant. So this will be k1, whatever is the value of the constant, and then 2 times that times the area. So geometrically speaking, it will be the area under this particular curve. But of course multiplied by 2. But other than that, that is what you will get here. So, but mathematically speaking, this is the expression that you get for the torque in the case of a multiply connected domain here. Right. And then now, if you use the relation that T is equal to tau n, then you will see that the surfaces phi equal to constant are traction free. Phi equal to constant are traction free. Free. So that is just you express n as the normal. So the n is going to be del phi by del x, comma del phi by del y. Correct? So that will be the normal, and then using the expression for the stress components in terms of phi, you can easily verify that the surfaces which are given there are traction free here. So del phi by del y times, so let us just do this. So that is tau xz times nx plus tau yz times ny is equal to, so this is tau xz is del phi by del y times del phi by del x minus del phi by del x times del phi by del y, and that you will see is equal to 0. So the surfaces phi equal to constant are traction free. This here actually you have to include one normalization factor. So this will be norm of n. So you can include that this norm of the so this let me just call it as a here. So this is actually norm of the vector del phi by del x and del phi by del y. So the norm has to be come in here. That is just a normalizing factor to make the magnitude of the unit normal as unity. But this is immaterial because finally we are just worried about the fact that this term is equal to 0. So you can see that if I draw now the surfaces phi equal to constant, then they are traction free. So suppose if I take this surface phi is equal to constant, and so any surface phi equal to constant is traction field. So that is just easily we can verify this on this one. Then what about the traction vector on the surface z is equal to constant. So let us write what the traction components are on z is equal to constant. So the surface, so this is the surface, z is equal to constant, let us say, okay, and then now the normal to this n will be equal to 0, 0, 1, and the traction vector will be given by t and this z is equal to constant is equal to tau xz, tau yz, comma 0, right? So just by multiplying tau with this normal, these are the traction components that you will get on a surface z is equal to constant, and this is equal to del phi by del y minus del phi by del x 0. So these will be the traction components that act on any surface z is equal to constant, and the magnitude of this shear stress will be given by, so the T now on Z is equal to constant will be given by under root of tau xz square plus tau yz square. So it is basically the magnitude of this particular vector that is acting on this surface here, and this is equal to square root of del phi by del x square plus del phi by del y square. So this is the magnitude of the shearing stress. This term is called as the shearing stress. So this is called as the shearing stress. Okay. And so this is the magnitude of that particular shearing stress that acts on this particular surface z is equal to constant here. Okay, and we have now this traction vector is tangential to the curves phi equal to constant. So this t on z is equal to constant is tangential to the curves phi equal to a constant. So let us see that. So suppose if I draw, so this line here we take as phi equal to 0. Now if you take this particular line phi equal to some constant, then what we are saying is that this t, right? So this t is of this particular kind, tau xz, tau yz. So this shearing stress on this particular thing is tangential to this phi equal to constant surface. That is because you can see that t dot n. So if t dot n comes out to be 0, then we know that this vector is tangential to this particular surface here. So t on z is equal to constant dot n now is equal to 1 by del phi times del phi by del y times d phi by dx. Del phi by del x. Del phi by del phi by del x minus del phi by del x times del phi by del y, and then that you can see is equal to 0. So all I have done is that the normal is the gradient divided by the norm of the gradient, right? So I have just substituted for that. So n is equal to del phi by norm of del phi. So I have just used that expression. So gradient of del phi will be del phi by del x, del phi by del y. Those are the components, and this tau xz and tau yz are given by del phi by del y minus del phi by del x. So I am just substituting del phi by del y minus del phi by del x. So finally this comes out to be 0. So what we have shown is that this traction vector that acts on this surface z is equal to constant is tangential to the line phi equal to a constant. Correct? So these lines are phi equal to constant are these lines here, right? And so phi equal to 0 is of course the outermost surface, and then you will get successive surfaces inside which are of the type phi equal to constant, and those lines so the traction vector will be tangential to each of these particular lines, as is shown here. Now we will show a very, very important result here. We will show that this shearing stress is a maximum on the outer bound. Okay, so this is a very, very important result. So no matter what the cross section is, whether it is rectangular or elliptical or any shape that you can imagine, the maximum shearing stress will always occur at some point. We do not know where that point is, but we know that that maximum shear stress will always occur on the outermost boundary. So let us show that particular result here. So the maximum shearing stress, that is this T, let us call it as max, occurs on the boundary C. So that is again, let me draw that. This is your A, this is your C. So it always occurs on C. So that failure of a bar under torsion, can be expected to initiate on the outermost surface, on the outer surface. We expected to initiate on the on its lateral surface, on its lateral surface. So this is a very, very important result. So let us try to prove this. So so we need this particular result in order to show this particular result here. So if phi, or let me call it as alpha, if alpha is not identically equal to a constant, and if 1 del square alpha is equal to 0, then alpha attains its maximum or minimum on C. And the second is that if del square alpha is greater than or equal to 0, so we say that alpha is subharmonic, then alpha attains its maximum on C. And third possibility is, of course, del square alpha is less than or equal to 0. Then in that case, it is said to be superharmonic. del square alpha less than or equal to 0. Alpha is super harmonic. Then alpha attains its minimum on C. So you have to remember that this is just a result from maths. Okay, this alpha is just some function, mathematical function, and so this result is from optimization here. That if del square phi is 0, then phi attains its maximum or minimum on C. If del square phi is greater than or equal to 0, then alpha attains its maximum on C. And if del square alpha is less than or equal to 0, then alpha attains its minimum on C. So basically what we are going to show is that this T max is a subharmonic function, right? So that means del square of T is greater than or equal to 0, and hence this T attains its maximum on C. So that is what we will now show. So need to show that T square is subharmonic. So actually, I mean, we can consider it as T square because if T is maximum, then T square is also maximum, or T square is maximum, then T is also maximum, because these are just positive quantities. We are just considering the magnitude of that particular vector here. So it doesn't matter if we consider the T square, if we try to do it for T square. So now let's find del square of T square. So that is equal to 2 times. So if you substitute now for tau xz, tau lz and so on, then you'll get del square phi by del x square. So this is after simplification. So this is 2 times del square phi by del x del y square plus del square phi by del y square plus del phi by del x times del by del x of del square phi plus del phi by del y times del by del y of del square phi. And we know that, let me just simplify this. So del square phi is minus 2g alpha. Del square phi is minus 2g alpha. So del by del x of this is just del by del x of a constant. And so these terms are going to go to 0. So only these terms will survive. So this is equal to 2 times del square phi by del x square plus 2 times del square phi by del x del y square plus del square phi by del y square. And so this is obviously greater than or equal to 0 because it's a sum of squares. And so from this we see that T square is a subharmonic function, and hence the maximum is attained on the boundary here. Now, so from our experience with circular cylinders, we know that the maximum shear stress always occurs on the outer boundary. So that is this one. So in a circular cylinder, we know that the shear stress varies linearly with R. Right? Suppose if R is that is your TR by J type of formula, we know that it increases linearly with R, and then the maximum is attained on the boundary. So in the case of a circular cylinder, we are already familiar with this particular result here. And so because in a circular cylinder it varies linearly with R, we may expect that the farther away you go from the axis of torsion, the more the shearing stress will be. So just to give an example, suppose if I take an ellipse which is subjected to torsion. So now in this particular case, your major axis is this one, A, and let us assume that A is greater than B now in this particular case. And now, so from this experience with the circular cylinder, intuitively we may expect that the maximum shearing stress occurs at A, because A is the maximum distance on the surface here, which is the distance of the periphery as measured from the center. So you can see that this point is at a maximum distance here, and so we would expect that the maximum shearing stress occurs at this particular point. But that doesn't turn out to be true. So all that we have shown in this particular result is that the maximum occurs on the boundary, but where on that boundary, that is something which only analysis can tell us. And so quite surprisingly, we will see that actually the maximum shearing stress occurs at this particular point, even though when A is greater than B. So this distance is actually smaller than this particular distance, but we will see in the next class that actually the maximum occurs at this the point on the minor axis and not on the major axis. So that is why you can see that this kind of a mathematical analysis is very important. One cannot go by intuition. So you can see that some of the results agree with intuition, but some others do not agree with intuition. And so this kind of a mathematical analysis is very important while studying these particular topics. So we'll continue this discussion in the next class.